Hello and welcome to the final lecture session of this course. It's about Boolean rings. A Boolean ring is equivalent to a Boolean algebra, and we'll see in this session that the algebra of sets is a Boolean ring. Let's start by really quickly reviewing what is a ring. Remember, a ring is a set with two binary operations that we'll call addition and multiplication. And the first operation must be an abelian group, that is a commutative group or commutative monoid with inverse elements and also requiring identity elements. The second operation, which would be the set with multiplication, is at least a semigroup, and the second operation distributes over the first operation. Now, the set that we operate on may also be a set of sets, like the power set that we talked about. In this case, our addition and multiplication would be operations on sets, like the union and intersection. Now, we saw that the real numbers form both a ring and a field under addition and multiplication. Now, what about the Boolean domain with the OR and AND operation, or Boolean addition and multiplication? Could this be a ring or a field? And we can also ask that same question for the power set of X along with the union and intersection operations, or set addition and multiplication. Now, it turns out these are not rings because the set with the first operation, which would be the Boolean domain, and the OR operation or Boolean addition, as well as the power set with the union operation, are commutative monoids because they lack the inverse elements on that addition operation. So we would need to find another operation equivalent to addition here that does have inverse elements to turn these guys into rings. So we saw that Boolean and OR operations do not have inverses. And we did have inverses on addition of the whole numbers because we had the negatives. And what if we took something like additional, unnatural, or whole numbers and just restricted ourselves to the numbers 0 and 1? And that doesn't work because of the 1 plus 1 ends up being 2, which is outside of our Boolean domain. And remember, the operation must be closed for all elements. So the result of the operation must yield an element that is within our domain. So 1 plus 1 would fall outside of it, and our operation wouldn't be defined on that input pair. So therefore, we can't do exactly, and that's exactly the reason why we didn't have the same type of addition as we saw on natural or whole numbers in the first place on the Boolean domain. Now, what we can do is we can actually fix this problem by introducing another type of addition called modular addition. And we'll talk about that next. So we'll define a new type of addition here called modular addition, also called rollover or wraparound addition. And effectively, if our result number from our addition operation is equal to or larger than the modulus, then we subtract a multiple of the modulus. So a good example is the 12-hour clock. The number 17 is what we call congruent to the number 5 modulo 12. So we end up subtracting 12 from 17 and end up with the number 5. So on the Boolean domain, we can define something that would be equivalent to addition modulo 2 on natural or whole numbers. So when we get to the number 2, we subtract 2 and end up with 0. That's our wraparound. Our modulus would be 2. It turns out that this exactly matches an existing Boolean operation called the exclusive OR or XOR operation. So the XOR operation produces the list of values shown here. 0 XOR 0 equals 0, 0 XOR 1 equals 1, 1 XOR 0 is 1, and 1 XOR 1 equals 0. So we'll use the XOR to build our ring. So if we define the binary operation O plus, that maps order pairs in B squared back to single elements in B, as the XOR operation, we can form our Boolean ring along with the multiplication operation that we already had defined as traditional Boolean multiplication. So the XOR operation, to carry it out, we can use the formula shown here. So XOR is equal to X and not Y, or Y and not X. So that yields the result XOR. And you'll get the same values we saw in the list in the previous slide. It turns out we now have additive inverses. The identity element for the XOR operation is 0, just like it is on regular OR operation. And it turns out that 1 XOR 1 equals 0, our identity, our additive identity, and 0 XOR 0 is also equal to our additive identity of 0. So the XOR operation has inverses for all elements in the Boolean domain, and it's allowed us to form the Boolean ring, which consists of the set of Boolean numbers with XOR addition and traditional Boolean multiplication as the AND operation. Now, if we're working with sets, we have an operation that's analogous to the XOR operation called the disjunctive union, also called symmetric difference on sets. So if we define our operation O plus as the binary operation taking ordered pairs in the Cartesian product of the power set of X with itself, that maps back to single elements of the power set of set X, then we can define our Boolean ring as the power set of the set X along with the disjunctive union addition and intersection, set intersection multiplication. And I'll end here with a quote from Wikipedia. An example of a Boolean ring is the power set of any set X where the addition is the symmetric difference and multiplication is the set intersection. So that should be clear to us now exactly what that means. So therefore, set algebra is a Boolean ring and therefore a Boolean algebra. Let's summarize this session. We saw that there is yet another type of addition called modular addition, and that the XOR operation as well as the symmetric difference of sets or the disjunctive union were in fact essentially the same thing. We were now able to see that Boolean algebra does form a ring with this operation, and that's because the elements of B are their own inverses under this XOR operation. So we have inverse elements, and that allowed us to form the ring along with the multiplication the way we had already defined it on Boolean numbers. And we saw that the same is true for set operations, and that the power set of any set X, the set of all sets or subsets of X, is also a Boolean algebra or Boolean ring.